Hello everyone. In this video, we are going to start study about the graph data structure. Graph is a data structure that has applications across computer science in multiple domains. So, it is really used across the industry in solving some real-world problems. Let us start the discussion about graphs with a definition of what a graph is. Graph can be defined as a collection of nodes. These nodes can also be known as vertices connected by edges. For example, let us consider some nodes. These nodes can represent any arbitrary kind of data. For example, let us have four nodes A, B, C and D, and let us assume that an edge between the two nodes implies that these two nodes are friends of each other. So here each node implies a person and each edge implies a friendship relation. So suppose this is our graph. In this particular graph, the nodes are A, B, C and D. Do note here that I have used curly braces here. Let me spend a few moments on differentiating between curly braces and parentheses. Pairs can be of two types. The first type is known as ordered pair. These are the pairs where order matters. For example, in this case, A comma B is not equal to B comma A because in this pair order is mattering and the first element in the left pair is not equal to the first element in the right pair. These pairs are represented by parentheses. The second kind of pairs are unordered pairs. As is itself explained by the name, the order doesn't matter here. Which means that A comma B is equal to B comma A. An unordered pair is represented by a curly brace. If you recall, this is also representation of a set. And also, as you might know, in set, order doesn't matter. Let us go back to our definition. We told that a graph is a collection of nodes. As I have represented the nodes by a set or by curly braces, this means the order of nodes doesn't really matter. We could have written this as P, A, C, D as well. Okay. So graph is a collection of nodes and edges. So if you see in this particular graph, we see that there is no sense of direction. There is no directed sign like A to B. So we see that these edges are bidirectional edges. For bidirectional edges, the order doesn't matter, and bidirectional edges can thus be represented by curly braces. So for this particular graph, our set of edges is going to be an edge from AB and an edge from AD. So we can represent edges as A comma B and A comma T. Great. So let us formally define graphs again. So graph is basically an ordered pair of vertices and edges. What I mean by ordered pair is that vertices comes first. So each of these vertices and edges are sets in themselves. So the above graph can be written as BACD and A comma B and A comma D. The graph data structure looks very similar to the tree data structure that you might have seen before, but there are some differences between a tree and a graph. Let us spend some moments discussing about those. In a tree, there is a rule of connection between two nodes. For example, in a tree, we remember there is an edge from parent to child, and there is only one incoming edge to a child. So, what are the total number of edges in the tree? Yes, it is equal to n minus 1, where n is the number of nodes of the tree. There is no such rule in graph. In graph, there can be arbitrary numbers of edges. There can be multiple edges to a same node. For example, let us draw another graph. In this graph, we see that there are three edges. Similarly, there can be an edge from the node to itself. This is known as a self loop. Also, there can be multiple edges between two nodes. Such a graph in which there can be multiple edges between a pair of nodes is also known as a multigraph. Great. Now, let us see some of the properties of the edges of a graph. As we saw till now, that the graph has no order or no direction of an edge. Till now, we have seen only edges like A to B, where there is no arrow. Such edges are known as undirected edges. Also, they are known as bidirectional edges. What bidirectional basically means is that, hey, in this particular edge, there is a relation from A to B as well as there is a relation from B to A. So, other than undirected edges, there are directed edges. Indirected edges, these are firstly represented using an arrow. So, suppose we have this particular edge. This means that there is a relation from A to B, but it doesn't mean that there is a relation from B to A. So, you might have graphs where there can be undirected edges, where you might also have a graph where there are only directed edges, or you might have a graph that have mix of undirected and directed edges. If a graph has only undirected edges, it is known as an undirected graph, or normally a graph. Whereas if a graph has only directed edges, it is known as a directed graph or a digraph. Great. Now let us study some of the real life use cases of graphs. As we discussed earlier, a graph can be used to represent a collection of nodes and any kind of relationship between those. Thus, graphs find a lot use case in social networks. Consider, for example, Facebook. In Facebook, each node can be a person. Let us say there are 5 people on Facebook: P1, P2, P3, P4, and P5. Let us say P1 and P2 are friends, also P1 and P3 are friends. Similarly, P2 and P4 are friends, and P4 and P5 are friends. Let us also say that P2 and P5 are friends. As you can see, this is nothing but a graph of nodes being P1, P2, P3 up to P5. Also, what are the edges of this graph? It's clear, it is P1, P2, P2, P4, P4, P5, P1, P3. 1, 2, 3, 4, 5. And also P2, P5. What we see from the graph of Facebook is that it has only undirected edges. At least that is true for the case of friendship relationship in a graph of Facebook. It might not be true for relationship of if a person likes a page or not. Can you tell me a graph that is not undirected for a social network? Yes, we can take example of Twitter. In Twitter, if a person A follows a person B, let us say we draw an edge from A to B if a person A follows a person B. Does this mean that B also follows A? No. So, in this case, we can say that Twitter has a digraph. Okay. So, due to this property that Facebook, Twitter, etc. can represent their data as graph, it allows all the graph algorithms to get applied on the problems that Facebook, etc. try to solve. Suppose Facebook has to solve the problem on suggesting some new friends to person P1. How might they do that? As you can see from the graph, P1 is already friends with P2 and he is also friends with P3. Who do you think we can recommend to P1 as his friends? One good use case or the friendship suggestions can be those people who are second level connections or second level friends to P1. What it means is that they are not friends of P1 but are friends of a friend of P1. So we see that P4 and P5 are friends of one of the friends of P1, which is P2. So we can recommend P4 and P5 to P1 as friend suggestions. This problem is nothing but equivalent to find nodes at shortest distance of 2. From a particular node. We will study shortest distance and all other things in detail in future videos. But this can be act as a good motivation of why graph is an important data structure to study. Also, another important application of graphs is in the whole internet or web. Have you seen pages? Whenever you visit a website, for example, you are visiting scalar.com. A scalar.com web page might link to another web page, let us say wikipedia.com. It might not be true that wikipedia.com is also linking to scalar.com, but Still, we get an idea that the hyperlink graphs of the web can be represented as a graph. This is actually the reasoning of the whole domain of web scraping and crawling. Let us think how Google would like to index the pages on the internet to show you search results. What they do is basically they start from a seed page. For example, let us say that their crawler starts from wikipedia.com. From wikipedia.com, they try to find all the links to different websites that are available there. For example, from wikipedia.com, there might be 5 different websites that are linked. Now, what crawler will do will iteratively visit each of those websites and then continue the process to further websites that are linked from those web pages. It also needs to ensure though that it is not entering a cycle, basically entering a web page that it has already seen, else the process will never converge. Also, as the number of pages on the web is a lot or almost in billions, this process, in the case of Google, would mostly be distributed. But ignoring the complexity of distributed aside, the problem of web crawling is equivalent to graph traversals. And we shall be studying those in depth also in the future videos. Before we end this particular lecture, let us actually study about other kind of graphs, which is weighted or unweighted graphs. Till now, we have seen graphs which can have directed or undirected edges, but there was nothing mentioned about those edges. Let us draw a sample graph again. Let us say this time we are drawing a graph of 5 nodes. Let us have some weights, or sorry, some edges. Suppose this time our graph is representing a road network of a city. What I mean by a road network is that if there is an edge from node A to node B, this means that there is a road from city A to city B. Thus, our nodes here are equivalent to cities and edges are equivalent to roads. Now suppose city A is Bombay, city B is Nagpur, city D can be Pune, and let us say E is Delhi, and C can be something like Calcutta. Now, do you think that the distance between Mumbai and Nagpur is same as the distance between Nagpur and Pune? Or is the distance between Mumbai and Delhi same as the distance between Mumbai and Pune? No. So in this case, it makes sense to actually put some information on the edge. This information might be something which mentions the distance between two cities or the length of the road connecting those two cities. So let me write some arbitrary numbers, and they might not be geographically correct or even far away from that. Let us say this is 5, this is 10, this is 8, this is 100, and this is suppose 1000. Here, each particular weight or information on the web on the edge is representing something extra about that particular edge. So, such graphs that have some information, normally an integral information associated with them, are known as weighted graphs. and edges that have that information are known as weighted edges. On the other hand, graphs that don't have any weighted edge are known as unweighted graphs. A normal Facebook graph can be considered as an unweighted graph. But suppose we had to add some kind of weights to graph. What might they represent? Let us say we decide to write weights on the Facebook graph to represent the closeness of friendship between two people. Suppose our modified Facebook graph is A, B, C, and D. Let us say A and C are friends, A and B are friends, B and C are friends, and B and D are friends. Till this time, this particular graph is an unweighted graph. Suppose I say that A and B are strong friends or are very close friends. We can actually use some numbers to represent the level of friendship between two people. So suppose A and C can be first one level friend, C and B can be one, B and D can be one, but A and B can be friends of level 2, which means they are very strong friends. So what we have seen till now is that graphs can represent very interesting types of data, and due to the graph algorithms, we can solve some interesting problems in the real domain. In fact, the whole study of all these graph problems is in a domain known as graph theory. We will be studying a lot of those interesting properties in our future videos. So make sure to subscribe to our channel to get notified when we launch the other videos on this particular topic. Thank you.